Thank you, Mark and Stuart, for putting on the conference and inviting us to speak. We're fortunate to have Yuval Cohen, the CTO and inventor of our technology, with us today. And in a couple of seconds, I'm going to pass him on and he'll go through the presentation. I just wanted to say a couple of things first. Our technology is a game-changing technology. We currently have a market cap of $550 million. There's a reason for that. We've raised over $40 million for the technology. Generally, it takes in excess of 10 years and $100 million to make a MEMS product. We've got there in around about 11 years, or hopefully get there in 11 years. We haven't spent $100 million, but we're fortunate, unlike a lot of other companies, but we're very fortunate. We've signed non-disclosure agreements with 120 of the top semiconductor companies in the world, from, you can work out, 1 to 120. And a number of those companies, some have made financial commitments, but a number of those companies have spent their own resources in assisting us to get to where we are today. We truly have, I believe, the only game-changing technology on the ASX. We only have 28 million shares. We don't have any options. And over the last 10 years, I'm proud to say we are the best performing stock on the ASX. So with that, I'll hand you over to Yuval.
Thanks, Fred. Thank you, everyone. I noticed we are the third MEMS company in this convention. Maybe not everyone knows what MEMS stands for. MEMS stands for missing every milestone. So, as Fred said, it took us quite some time to reach this point. We are not quite there yet, but we are very close. What we're doing is we are building a speaker on a chip. The speaker is a MEMS speaker. There are a number of reasons to do that, number of advantages, but we recognize that speakers, loudspeakers, are the last analog component in the consumer electronics hand, user's hand. In a mobile phone, the picture is digital, the data is transferred digitally to and from the phone. Microphones today are digital, but the speaker is always analog. And for the past 100 years or so, the advancements in speaker technology were primarily small and incremental, better materials, better designing methods, but the fundamentals of the analog speaker hasn't changed for 100 years, and that's the space we're working on. We are implementing a technology called DSR. DSR stands for Digital Sound Reconstruction. It's fundamentally different from any analog speaker. This slide illustrates how this basic concept works. An analog speaker generates sounds by moving a membrane. The membrane pushes the air, it generates a pressure. The pressure propagates through the air and reaches our ear, and that's the sound that we hear. DSR is a technology where instead of one membrane, you have an array of identical elements. The elements are individually controlled, and they can move up and down very rapidly. When they move, they each generate a small burst of pressure, either positive or negative if it's moving up or down. We move these elements, we call them pixels, AudioPixels. We move them in groups. If we move a larger group, we get a stronger pulse. If we move a smaller group, it's a smaller pulse. And instead of generating this the curve in the fundamental audio frequency, we generate a sequence of pulses. It happens at a very rapid rate, typically around 100 kilohertz. Well, in the ultrasound, people can hear up to 20 kilohertz when they're young. Later, it deteriorates. And our ears actually can't react so fast to the rapid changes in pressure. Our ears work as low-pass filters, and they detect the envelope. And the envelope is exactly the same as the sound that we're trying to produce. You can think of it as instead of with an analog speaker, you're trying to change the amplitude. That's the only degree of freedom that you have. We're actually changing the surface area of the membrane of the speaker as it changes over time, and that's what changes the pressure. This slide shows the basic structure. On the left, you see a packaged chip. It includes a few pieces of silicon. The major one is the MEMS transducer. It's a relatively large chip, about 100 square millimeters. So the guys in the know can calculate how much it relatively costs. Next to it, we have the driver. Our MEMS chips requires high voltages to operate. The driver sitting next to it actually generates the high voltage, and it switches the signals to the different pixels. We designed this thing to operate in a consumer electronic product. So we can work with a wide range of voltages from 2.5 volts up to 25 volts. So it's suitable for mobile phones, for tablets, for PCs, for TVs, automotive, etc. Regardless of what voltage you have available, the chip would generate whatever voltages it needs to operate. It's in the range of 80 volts. On the right, you can see the construction of one of those pixels. We have a few static layer and one active or one working layer. It's a thin sheet of silicon, that's the membrane layer, where we etch springs, small springs called flexures, and the membrane is now free to move up and down. And by applying voltages between the membrane and one of the electrodes, we can pull the membrane up or down and generate the pressure. Other than being cool, we actually have a reason for trying to do that. There are a number of advantages derived from this basic technology. All of these advantages, you get it's a package deal. You get all of them. Some markets are really keen about quality. Others really like the power efficiency of this product. But you get all these different benefits when you use our chip. There are a couple of performance advantages. First of all, from the same surface area, we can usually produce sound with a much wider bandwidth. We can extend between 2 and 3 octaves below the cutoff frequency of an equivalent analog speaker. If you, for example, you look at a mobile phone speaker, the speaker you have there today is capable of producing sounds between 1 kilohertz and 15 kilohertz. The human voice range extends down to 300 hertz. That means that the speaker cannot faithfully reproduce our voice. And there is no real way to improve that with the size available in a mobile phone. Our chip, the same size, same surface area, can produce sounds down to 250 hertz. So we can cover the low frequency range as well. And on the high side, we can produce frequencies up to 50 kilohertz. That's in the deep ultrasound. And that has other applications, not related to music, but things like sensing distances. There are applications in gesture control. There are communication applications where we can transfer data from point to point ultrasonically so it doesn't disturb the occupants. That's the bandwidth. We also have a distortion advantage. With small speakers, it's very hard to get clear sound. You can all attest that the sound quality of your mobile phone is not as good as your car stereo or your home stereo. The one easy metric is a parameter called THD, total harmonic distortion. It's an indication of what percentage of the signal of the sound coming out of your device is the actual sound and what portion is distortion. And typical numbers for a mobile phone are between 10 and 20% distortion. In a high-end home audio system, it's about 1%. In a car, it could be between 1 and 2%. Our chip can produce sound with distortion levels that are roughly 0.02%, well below the detection threshold of our ears. It means that you won't be able to distinguish between a live singer and a singer recorded and played back over our chip. The distortion is negligible. Complexity, that's a bit misleading because it's quite complex to make our chips. But once we do, we intend to sell our customers a chip, which would be, he would buy them using the same distribution channels as he buys his RF or Bluetooth chips or the application processor, any other chip. You buy the chip, you have a data sheet which would describe exactly what type of performance you can expect from this chip. You don't need to invest a lot of effort into designing the enclosure. In an analog speaker, the enclosure is responsible for most of the character or most of the performance of the speaker, and it's very difficult to design a good enclosure. You can see that consumer electronic companies, once they optimized and designed the sound module, the speaker and the cavity, the enclosure, they transfer the same module from model to model, from system to system, because it's very difficult to design and optimize this thing. In our case, you have an Excel spreadsheet. You punch in what is the required bandwidth, what is the required sound pressure level, volume that you need, and it will tell you how many chips and how to configure them. On the left side, one obvious advantage is the form factor. I have a box here with a few speakers. This is the speaker of the future. It would replace, this one would replace a mobile phone speaker, but if you're looking to replace a home stereo sound system, imagine you have a big box, a subwoofer, many speakers, and you can get performance which are equivalent with something the size of a business card. A bit thicker, but that's roughly the size. We consume about 90% less power, and that's important for every battery-operated device. It's much more efficient. The main reason is not the efficiency, necessarily the efficiency of our device, but the inefficiency of analog speakers. Analog speakers are capable of basically converting 1% of the electrical power into acoustical energy. The rest is wasted as heat in the circuitry and in the voice coil of the speaker. There is a parameter we call modularity. Effectively, we plan to produce only one product, one chip size for every application. The way to scale the performance is to use multiplicities of that specific chip. Every time you double the number of chips, you extend the bandwidth by 1 octave. So if you use 2 chips, you can go down to 125 kilohertz. If you use 10 chips, you can go down to 25 hertz. Okay, it's completely linear. And you can, based again on this Excel spreadsheet, you can design the sound that you need very easily. The markets are numerous and large and big. We are not sure where we're going to start. It's our biggest challenge right now is once the technology is stable and available, is ramp up. The chips are rather large, and that means that we need to process a lot of wafers in the fab to get significant quantities. It's very difficult to go from 0 to 100 million chips, which is what's required if we win a mobile phone model. So we'll probably start with the application that has less units, and it would allow us to ramp up a little bit slower and wet our feet gradually. These are some of the markets. I'm not going to go over them. The total available market, annual market for us is roughly 10 billion chips. It's going to be a little while before we get there. In terms of IP, currently we have over 130 patents worldwide. We are practically the first to enter this market. There were a few attempts to build DSR speakers in the past. Actually, the first concept was theorized by Bell Labs in the 1920s or 1930s. But before the invention of MEMS technology, it was practically impossible to manufacture these things. We were the first to enter this market with significant effort and budget, And we were lucky to secure many different aspects of the technology, even trivial things like how to control the volume of a digital speaker. In an analog speaker, you change the gain on the amplifier. That's easy. On a digital speaker, the amplitude of these elements is fixed. You need an algorithm, a software implementation to change the volume. It's not very clever, but we are the first to think about it. So we have a patent on volume control. We have patents on the fabrication methods, on the structure. There are a lot of aspects of the software that controls these speakers, which are patented. If you're familiar with a term called the phased array, it's a technique used to direct beams of sound or radio waves by implementing phase changes between multiple transducers. And we can do that with our chip. We can control the directivity of the sound. We can make the speaker very narrow and transmit the sound in one direction, or make it very wide, and then it's being heard everywhere. That's mostly relevant if we have more than one chip. With one chip, it's very difficult to control the directivity in low frequencies, but it is easy to do it in the ultrasound range, which, as I said, there are applications for that. So we have a whole range of patents on software to control these chips. And what else? Yeah, those are just the list of some of the fields and of our patents, but there is a lot of know-how behind this, which is not patented as well. We've been working on that since late 2006, and today we have a number of partners, large partners, manufacturing partners, who help us build those chips. We've been able to produce sound from chips in 2009. That's the first time a silicon chip played sound. And we've been working on productization of the technology since. The first prototypes we built were based on expensive fabrication techniques, prototyping techniques that weren't suitable for mass production. In the past decade or so, we've been focusing on mass production of our chips. Today, we're working with a couple of large fabs, and we actually prototype in their in the mass production facility. It's, as was indicated before, it's not trivial. People who have machines that generate money pretty much reserved and reluctant to let people play with those machines and do R&D on them. So we were lucky to have very, very good partners who see the potential of this technology, see the potential of orders that they can get, and they let us play with the facility and equipment. That's a general overview of the company. We have a R&D facility in Israel, and we have the parent company is here in Australia. It's listed in the ASX. The symbol is AKP. Maybe Fred would like to say a few words about the market and no? Okay. Ian. All right. And that's it.
Thank you. Thank you very much.
Thank you.
And we'll go over to a few questions.
Okay. Yeah.
Take us back to 2005 or thereabouts. Take us back to 2005. What caused you to first think about the potential for this technology?
You know the game Reversi or Othello? That's the trigger. Othello is a board game where you have black and white pieces, and you can very quickly change the color of the board from black to white if you make the right move. And I thought of it, I like to play Reversi, and my career is in the acoustics and audio. And I was thinking of speakers and the board changing color all of a sudden. I thought, I have individual elements, and the whole thing becomes white, becomes black. I can change the whole color by controlling a few pixels, and that was the trigger. I later discovered that I wasn't the first to think about it. As I said, Bell Labs were playing with DSR a long time ago, but at the time, the smallest speakers they could find were 20 or 30 millimeters in diameter. And when you play with the acoustics, with the math, very quickly you discover that in order for this thing to work, the size of the individual element must be much smaller than the wavelength. And with audio, 20 kilohertz audio, it's about 3.4 millimeters, which means the maximum size of your speakers or elements can be about 0.5 millimeter. And that basically was the end of that project. As soon as they realized that, it was no longer feasible to build it. But today, MEMS is available. Our small structures are about 200 microns in diameter, each one of our pixels. And they move up and down about 6 microns, not too much, but it's enough to produce sound.
We had a question over here.
Yep.
Who are your manufacturing partners?
There are a few. There is one I can talk about. That's Tower Semiconductor, Tower Jazz. They have a few fabs around the world. We're working currently with the fab in Israel. But mass production would probably expand to some other fabs as well.
So just one other question. How close to commercialization do you think you are?
That's a difficult question. We just in the past couple of weeks received, I don't remember, the 50th or 60th iteration of wafers. It was quite challenging to get the wafers to work properly. We had issues with manufacturing. There was an issue with the long-term reliability. And I'm happy to say that we solved all the big problems. Right now, we're at the step of stabilizing and qualifying the process. At that step, our fab actually goes through the 500 and 600 different process steps. And for every step defines the corner cases, what are the possible tolerances. So they're running more and more wafers through the fab in order to determine what is the working window or the tolerance window for every step. And that's basically an effort to increase the yields. And once that's concluded, we can start mass production. Okay.
If there are no more questions, I'd like to thank you very much for your presentation.